Hello everyone, this is the Kalman filter summarized, and some good background knowledge would be state space modeling and the multivariate Gaussians, though I will lightly cover it now. And what multivariate Gaussians are is probability distributions in multiple dimensions. And for example, a 2D probability distribution would look like this. And this is and a 1D version of this would be the commonly known bell curve. And what the multiple dimension distributions use is a covariance matrix. It basically uses the variance and covariance as just one thing, and what the variance is, it simply signifies by its name is how the variable varies, how one variable varies amongst itself. And what the covariance usually signifies is some correlation between two variables. And these things are put in a matrix seen here as sigma. So as you can see, the diagonal is having the variances, and the other parts is having the covariances. And this is how the 2D would look like, seen by the image here. And actually changing the covariance can gives a sort of effect of thinning out our Gaussian. And the Kalman filter essentially, it looks like this, but it is not matrix multiplication. It's actually leverages the Kalman gain to achieve something similar, in the sense of making the covariance, not the covariance, but like the hill sharper. As you can see, this image, if we would apply the Kalman filter, it would get sharper and sharper, hopefully. That's the plan with the Kalman filter, to reduce the error. So how does this work? It works with the update and predict step. And we actually start off with the predict step. And what the predict step has, by the way, refer to the multivariate table, because that's what we are using. And what it does in the first equation is our model. So this you will get from some sort of a mechanical ODEs, ordinary differential equations. You have to know state space modeling. So you would make a continuous state space model normally, or commonly, more commonly, and you would discretize it by some common method like zero order hole, or some other method if you'd like. And then you can get this form here. And through some experiment, you can construct the covariance matrix P. And as I've shown how a covariance matrix looks like, it has the variances and covariances. So this you will get experimentally from your model through some simulations, like an Excel table, and using some Python script to, get to the actual matrix. And you don't necessarily have to do that way, but essentially you will have to accumulate data. And then you can get your initial covariance matrix for your model. And then you use the FP transpose F to essentially move it forward in the time step. So it looks like this image here. It's not no correction is applied, it's simply moving through time. So this is because the Kalman filter has to, be dynamic, of course. And we have the element Q, which is the noise, modeled noise, or not necessarily noise, but just unmodeled dynamics that go into this matrix. And I won't get into how this works. You can check out my GitHub, but there are just a lot of different methods, and there's no one set method to use, so you can just check out the link in the description. And for the update step, so we compute, our x and our p, so our state and then our covariance, moving in the one time step. And after that one time discrete time step is applied, we have the update step. And the update step is summarized here in the multivariate table. And here we have our measurement z minus our matrix H, which is to basically change units. So if you have, because we are calculating a residual here, an error y, and we need them to be the same units. So essentially this is dependent on what system you're having, and just context dependent. And this is the equation for the Kalman gain. So we use the Kalman gain, and what the Kalman gain has is the calculated model covariance and the measurement function, the one that converts units, and then the R, which is our measurement noise. Yeah, it's the measurement noise. Covariance, so this is basically the uncertainty of our measurements, and this is also found experimentally. So for example, the Kalman filter equation uses a covariance matrix R, the measurement noise matrix, and it will have the dimension m by m, where m is the number of sensors. It has the covariance matrix to account for correlations between sensors, and also like see their means as well. So basically what you would do is you would run the sensor, accumulate data, and then find the average, find the means, put in diagonal, and also the covariance. So similarly to how you would find P, you also find R. Yeah, so with the residual and the Kalman gain, sorry, my trackpad. So with the residual and Kalman gain, you apply that to the state, and then you get the corrected state. So the update part is a correction step, and the predict step is the moving forward in time step. That's how I would, summarize this. And our model covariance, so our Gaussian from our model, also changes, and it uses this equation here, and this is not the commonly known equation seen over here, because we use the Joseph equation. And the only point of the Joseph equation is that you will not encounter like errors, because the original equation to get P from the update step can cause some floating point errors and non-symmetric matrices, so you can encounter problems. So you can use the more stable Joseph equation. So essentially what is happening is that you get a less of an errorful Gaussian, like seen in blue here, and you feed it back again to the predict step, so it moves it forward in time and then gets corrected again. So you move it forward in time, correct it again, move it forward in time and correct it again. And that's all you have to need to know in this summary. If you would like to look more, you can refer to my GitHub and also the Kalman Filter Python book, also linked below, which is actually how I learned the Kalman filter. One last thing to add about the Kalman filter is the literature notation. And in the literature, we have a k to the left and a k to the right separated by a vertical dash. And the k to the left describes the discrete time step in general, and the k to the right describes the more of the step in the algorithm itself. So yeah, that's how it is.